body emission or continuous emission, same thing, they're synonymous with each other. Oops, or a rainbow. Okay, not a rainbow. Again, official Hollywood character. I've seen students make that mistake. It's very messy. Yeah. So hot gas at high density or pressure is going to go with a continuous vector. But a hot gas at low density is just going to give you emission. Right? That's the distinction I'm talking about. So that's Kirchhoff's first law. And okay, black-body radiation, this is what gets produced in that situation I was just talking about. Kirchhoff's second law, which is also known as Kirchhoff's law number 2. And that one refers to something that we have talked about, which is just that if we have hot gas at a low pressure, we get emission lines. So there you go, bang, bang. Hot gas, 2 different scenarios, first law, second law. First law was a new one for us, hot gas at high density, get a continuous vector. Hot gas at low pressure is going to produce emission lines. So that's what's happening in the bulb here. Hot gas at low pressure. Okay, so what's the difference? Well, the difference is that because we have low pressure, we're not disrupting any atomic structure. We have nice, separate atoms that are intact, they're not ripped apart or anything like that. And what we do is we bump them together gently. The collision leads to excitation. We talked about this. We heat the gas just like what we have in the bulbs upstairs there. We're heating them by arcing them with electricity. But basically causing them to get hot and bump into each other. When they bump into each other, some of the kinetic energy gets converted into excitation energy. So if we think of these as fast-moving atoms at first, right? Now they're slower-moving atoms. Because some of their kinetic energy got converted into excitation energy. Now they can de-excite and emit radiation. So this is exactly what's going on in the tubes. We're heating the gas in the tubes using electricity. They bump into each other, which causes excitation. They de-excite by emitting the radiation. The radiation comes out, and all is good. We use the radiation to see things. So this process is going to convert heat into radiation. By that I mean the heat energy is that kinetic energy of the motion, right? You have a hotter gas, you have faster random motions. So what we have here is a decrease in the speed of the motion because some of the heat energy is being converted into radiation. And so the gas is going to cool down when the radiation escapes, unless we keep heating it. So the gas in the tubes doesn't actually cool down because we're constantly heating it. And there's actually a balance between the heating from the electricity and the cooling coming out in the radiation. There's a balance between those two. So everything is maintaining a fixed temperature in those bulbs. But of course, obviously, if you turn off the AC, alternating current, the bulbs are going to go out, right? Why do the bulbs go out? Because the gas cools off. That's the end of the story. So this is basically the process where we convert heat energy into radiation. Okay, Kirchhoff's third law is known as the one that comes after the second law. And that one is that a cool gas at low pressure is going to produce absorption lines. So, of course, we've already talked about this. This is, again, if you back illuminate a cool gas, you get absorption lines on the other side of the sample. So here is just another little one of my dramatizations of what happens when it gets like that. So here we have a person, I think this was a student volunteer, observing a hydrogen atom in the ground state. Okay. Now he's actually, I forgot to mention this, but he's actually been conditioned to experience pleasure when he observes green light into his retina. Kind of a weird thing. Again, pre-internet, we never know this anymore. But, okay, so here's the yellow photon, green photon. Yeah, so he didn't know about this whole absorption thing. The colors are a little weird, but in this case, it's the green that actually caused the absorption. So he's expecting this green photon to come in, and it's kind of sad. I don't really remember what that means anymore, the reference to the party, but anyway. So what happened here was that the photon was redirected. The photon was going from left to right, it causes excitation, and now it gets sent in a new direction. So what this fellow here is going to see is an absorption line. Because again, he sees that dirt of that color, right? Because they pretty much get redirected. Now we're going to talk a little bit about how we can use all this to identify atoms. So we talked about how the basic atomic physics leads to the creation of emission lines, absorption lines, and continuous spectra. Now we're going to talk about what if you see a certain pattern through your telescope. Well, when you look at your telescope, you're not going to see this. If you look through a normal eyepiece, you're going to see a little star, you're going to see a little pinpoint of light. But you actually can take a prism and slap it on your on the eyepiece of your telescope. You want to do that, and project the light of the star through the prism onto a little screen. It's going to be pretty weak unless you have a big telescope. So that's one of the reasons astronomers use big telescopes. But when you project the light through the prism attached to the eyepiece, you can actually see a pattern like this. Okay, so suppose we see this pattern. Now, the laboratory spectrum of hydrogen gas is 400. So this basically is the laboratory spectrum. They're both the laboratory spectrum of hydrogen gas. I just kind of simplified it down here. We're going to focus on these 4 lines. There's quite a bright red line. That's the main line at 6,563 angstroms. That's the red line we keep talking about when we talk about hydrogen. And there's this triplet down here. Okay, so they have definite wavelengths. So if we take hydrogen gas, we heat it up in the laboratory, and we pass it through a prism, we see this pattern at those wavelengths. So we call that being in the rest frame of the emitting hydrogen. We're not moving with respect to it. It's sample sitting right next to us, no motion. We see those wavelengths. But remember, we talked about this idea of the Doppler shift and how the wavelength of the emission that's perceived by the observer depends on the relative velocity of the observer and the source of the radiation. All right, so suppose now we look through our telescope and we see these wavelengths. Now remember, when we looked at hydrogen in the rest frame, the red line is at 6,563 angstroms. But when we look through our telescope, we see it at 6,945 angstroms. But we recognize this as hydrogen emission because the overall pattern is the pattern or fingerprint of hydrogen gas. No other element produces that pattern of lines. It's again the fingerprint idea because of the different electronic structure. Okay, so we look here and we say, that's hydrogen. And then somebody taps us on the shoulder because it's probably 3 o'clock in the morning. Astronomers don't sleep, right? Doing calculations at night. And somebody says, well, wait a second. If it's hydrogen, how come it's at 6,945 angstroms instead of 6,563? Like what we would expect to see in the laboratory. Okay, well, what's the answer here? Remember, the Doppler shift is going to cause a redshift or a blue shift depending on whether the source of the emission is moving towards you or pulling away from you. If it's pulling away, we get a redshift, which is an increase in all the wavelengths. Okay, so that's clearly what we're seeing here is a redshift. A redshift means that the wavelength is perceived to have increased. So what we see qualitatively is that this is a sample of hydrogen gas that's moving away from us. So if this is a star, as I say here, it's a stellar spectrum. So we look at this and we say, okay, well that star is moving away from us because it's a pattern of hydrogen, but it's been redshift. All the wavelengths have increased. And by the way, it's not just this one wavelength that's increased, all of them have. Like this one here at 4861 is now at 5144, etc. So it's a redshift. Qualitatively, the star is moving away from us. We can actually go farther than just a qualitative statement because, of course, of your friend mathematics, which is going to allow us to relate the emitted and observed wavelengths to the velocity, actually compute the velocity of recession of this star away from us. So here I've just summarized stuff in a little table here. The emitted wavelengths are the wavelengths we would see if we were sitting stationary with respect to the hydrogen, or if the star weren't moving. Here's our 65, 63 angstroms for the red line again, right? And each of these wavelengths is paired with its associated wavelength in the redshifted spectrum observed. So this is the observed spectrum, 6945, the emitted spectrum. Well, how do we know that's the emitted spectrum? We know it's the emitted spectrum because we recognize that it was a pattern of hydrogen gas. So from that fingerprint, we know it's hydrogen. We know hydrogen's strongest line is the red line at 6563. So we know what the actual intrinsic wavelength, the emitted wavelength, actually is in this case. Now, all of this is related to the velocity of the source through this formula, which I flashed by you quickly before the first exam, but it wasn't on the first exam. I just kind of showed you how this works a little bit. So basically, we're going to apply this now in the second exam. Because I've had all sorts of complaints about not enough math in the first exam, so I'm going to be sensitive to that. So here's our observed emitted wavelength. And now, I'm not going to go into where this formula comes from, but again, I'll just suggest to you that at least qualitatively it does make sense. Because this V over here is the speed of the source relative to you, the observer. So if I pull my laser pointer back, it's a red laser pointer, if I pull it back, that would be a positive velocity. So, if I could pull back fast enough, you wouldn't see red light anymore. It would actually be redshift if it's gone infrared or something like that. But anyway, the definition here is the velocity there is positive for recession away from you, and negative if the source is approaching you. Okay, so there's a sign convention on that velocity. And C is the speed of light. Now we have the observed and emitted wavelength. So the emitted wavelength is like that 6563 for the red line, and the observed is like the 6900 angstroms for the red line. All right. So qualitatively, if the observed is larger than the emitted, then the velocity has to be positive because we have to multiply the emitted by a number bigger than 1, if we're going to get the observed. Because the emitted is 6,500 and the observed is 6,900. So, we have to multiply by something that's bigger than 1. So the velocity there has to be positive. If it was negative, we'd be multiplying by something that's smaller than 1, and that would create a pollution equation. So anyway, qualitatively, you can see that if this velocity is positive, it will create a redshift. That's my main point here. If the velocity is positive, then this entire thing in parentheses here is bigger than 1, so the observed wavelength is bigger than the emitted wavelength, and that's a redshift, right? So if the velocity is positive, it's definitely going to create a redshift. Now, we can actually compute the velocity because of the table that we just talked about of the emitted and observed wavelength. Well, okay, so we're just ranting on and on a little bit here. Same formula, go a little bit further now. All right, so here's the table. So I just reconstructed the table of the emitted and observed wavelengths, but now we've also got the formula there. Okay, so again, here's the red line at the bottom. The intrinsic wavelength is 6,553 angstroms. We observe it to be 6,945 angstroms. It's definitely a redshift. The velocity is positive, but we can compute what it actually is now. Because suppose we take one of these numbers here and divide it by one of those numbers. If we divide a left-hand wavelength by a right-hand wavelength, that's like dividing by lambda emitted. We're going to isolate that 1 plus v over c factor. And if we actually carry that out for any of these pairs, what we find is that v over c is 0.058. So you can check this yourself. If you put 0.058 in v over c there and do the math, you can multiply any of these numbers by 1.058 and get that, like 6563 times 1.058 is 6945. So the multiplication factor is 1.058. So the v over c is just 0.058. So look what we've done here. We've identified the sample as being hydrogen. We know what the actual emitted wavelengths are because we know it's hydrogen. We can look at hydrogen gas in the laboratory. So we can make this table and we can actually compute the velocity. So this is the case where we've now computed the actual velocity of that star to be a recession velocity away from us at about 5.8% of the speed of light, or about 17,000 kilometers per second. Right? That's a pretty healthy velocity for a star in our galaxy, actually. But anyway, what we've done is we've measured the speed of the star. So the bottom line of this whole thing, oh,